Hello everyone, I am Prakhyath, Assistant Professor, Department of Mechanical Engineering, AJIET Mangalore. Today I am going to discuss about Module 3 of Fluid Mechanics. This is a Class 1, Fluid Dynamics. So in Fluid Dynamics, I am going to discuss about Introduction, Forces acting on fluid in motion, Euler's equation of motion along a streamline, Integration of Euler's equation to obtain Bernoullis equation, Assumptions and limitations of Bernoullis equation, Introduction to Navier-Stokes equation, application of Bernoullis theorem such as venturi meter, orifice meter, rectangular and triangular notch, and pitot tube. So first let's go for introduction. So before going to introduction, let us just recall concepts of second module, that is fluid kinematics. So what is fluid kinematics? Fluid kinematics is a study of fluid motion without considering the forces that causes the flow of fluid. But this dynamics, it is exactly reverse as that of fluid kinematics. That is, dynamics of fluid flow is the study of fluid motion with the forces causing the flow. We are considering forces that causes flow of fluid in fluid dynamics. But in case of kinematics, we are not going to consider the forces which causes the flow of fluid. There is a difference between fluid kinematics and fluid dynamics. The dynamic behavior of the fluid is analyzed by Newton's second law of motion, which relates acceleration with the forces. So from Newton's second law, that is F equal to ma, we can get correlation for force in terms of mass and acceleration. So m is the mass, a is the acceleration, and F is the force. So we can get force from Newton's second law of motion. The fluid is assumed to be incompressible and non-viscous. So we have to make some assumptions in deriving the expression. First assumption is incompressible. So density remains constant. We cannot compress the fluid. So density is not going to change. And non-viscous. Viscosity means is a resistance to flow. Non-viscous means it is not going to offer resistance to flow of fluid. So there's a thing here, incompressible and non-viscous. So equations of motion. According to Newton's second law of motion, the net force Fx acting on a fluid element in the direction of x is equal to mass m of the fluid element multiplied by Ax in the x direction. So in order to get force in the x direction, say in x direction, that force is given by Fx, that is equal to mass into acceleration in the x direction. So Fx equal to m into Ax mathematically. Take it as expression 1. In the fluid flow, the following forces are present. So in fluid flow, we may have following forces. First force is gravity force, that is Fg. That may be due to weight of the element or fluid. Second one, pressure force. Pressure is given by P equal to F by A. So we can get force by multiplying pressure by area, P into A. So pressure force PA, Fp. Then force due to viscosity, that is Fv. If the fluid has some viscosity, then we get the force due to viscosity, this is Fv. Then force due to turbulence. If the flow is not laminar, then we get force due to turbulency, that is Ft. Then force due to compressibility, so that is Fc. So if the fluid is compressible, then we get force due to compressibility, that is Fc. So therefore the net force in the direction x, Fx equal to Fgx x plus Fpx plus Fex plus Ftx plus Fcx is a summation of all 5 forces in the x direction. We have to consider x component. So because it's a force acting net force in the x direction. If the force due to compressibility Fc is negligible, then resulting net force Fx equal to Fgx plus Fpx plus Fex plus Ftx, and equation of motions are called as Reynolds equation of motion. In net force expression, that is Fx, if Fc is 0, then resulting equation is called as Reynolds equation of motion. Similarly, if Ft is negligible, force due to turbulency is negligible, then resulting equation of motion is known as Navier-Stokes equation. So then if the flow is assumed to be ideal, so ideal case viscosity is 0. So viscous force is 0. So force due to viscosity is 0. Then resulting equation is known as Euler's equation of motion. So these are three expressions. Reynolds equation of motion. For Reynolds equation of motion, Fc is 0 or negligible. For Navier-Stokes equation, Ft is 0 or force due to turbulency is 0. Then for Euler's equation of motion, viscous force, that is Fe is 0. Then Euler's equation of motion. This equation of motion in which the forces due to gravity and pressure are taken into consideration. Here we are considering force due to gravity and force due to pressure. So these are two forces in that out of 5 forces. This is derived by considering the motion of fluid element along a streamline. Consider a streamline in which flow is taking place in x direction as shown in figure. So fluid is flowing in x direction, some direction S. So consider a cylindrical element of cross section dA and length ds. So we can have fluid element here. It's a cylindrical element of cross section dA, small element, and length, as we can see there, ds. So then the forces, different forces acting on this fluid element are: one is pressure force, that is pressure equal to F by A. So in order to get F equal to P into A. So area is small cross section, so dA, P into dA in the direction of flow. So flow is happening in the S direction. You can see the streamline S direction. Then in the direction opposite to the flow, that is on the upward phase, P plus dou P by dou S into ds into dA. There is another pressure force opposite to the direction of flow. So P plus, there is a variation of pressure with respect to height. The height or length is ds. So variation of pressure is dou P by dou S multiplied by height or length of that fluid element, that is ds. We have to get pressure force, so multiply by dA. So P plus dou P by dou S. Dou P by dou S is a pressure variation with respect to a fluid of element ds into dA. So this is acting on opposite direction. Then there is a weight for that fluid element. So weight is acting vertically downward direction. So weight, as we all know, weight equal to W equal to mg. So how to get expression from m in terms of density? So that is density equal to mass by volume. So mass equal to density into volume. Now volume can be obtained by multiplying area into thickness. So area is here dA and the thickness or length is ds. So dA into ds into rho. So that is mass. So in order to get weight, you have to multiply mass into g. So acceleration due to gravity. So rho into dA ds into g, that is the weight of the fluid element. So the forces acting on cylindrical element are pressure force PdA in the direction of flow. So that is pressure force acting in the direction of flow. Pressure force P plus dou P by dou S into ds dA opposite to the direction of flow. You can see in diagram. Then weight of the element rho g dA ds, because W equal to mg, but m equal to density into volume. Density is rho and the volume can be obtained by multiplying area by the length dA into ds. So rho into dA ds, that is mass, into g, that is weight of the element. Let theta is the angle between direction of flow. Direction of flow in the sense it is in the direction of S, and line of action of weight of element. So along with the line of action of element, there's a weight of the element we have to consider, and in the direction of flow we have to consider theta. So we can see how figure B. So ds is the direction of flow and dz is the line of action of weight of the element. So there is an angle theta in between. So there is a fluid element, small fluid element, so with the angle theta. The resultant force on fluid element in the direction of S must be equal to mass of fluid element into acceleration in the direction S. So this is similar to Fx expression. Now we have to get a force in S direction because flow is happening in S direction. Fs equal to m into As, acceleration in S direction, and again it is multiplied by mass of the fluid element. So that is equal to net force. Net force is we can obtain from figure A, that is PdA in the direction of flow. So it is positive. So PdA minus P plus dou P by dou S into ds. So it is opposite to the direction of flow, so it is negative, into dA. So minus P plus dou P by dou S ds into dA minus. So now we have to consider here weight is acting vertically downward direction, but we want the component of weight with respect to some direction. Yes, so it is actually we have to resolve that force or weight into x component and y component. So we are going to get in the direction of S, we are going to get rho g d a ds ds into cos theta. So we have to consider cos component, cos theta along the direction of S. So minus rho g dA ds cos theta, that is opposite to the direction of flow, so it is minus. You can resolve that force into two components. So upon resolving, we have to consider a cos theta component along the direction of S. So rho g dA ds cos theta equal to rho into dA ds into as. Mass can be obtained by multiplying density by volume. Volume is dA into ds, so density is rho. So rho into dA ds into as, where as is acceleration in the direction S. Now as equal to as equal to dv by dt. As we all know, acceleration is rate of change of velocity. So where v is a function of s and t. So velocity is a function of two coordinates, that is a function of space and time. So space coordinate and time, v equal to f of s comma t. So for that type of function, we can write expression as as equal to dv by dt equal to dou v by dou s ds into ds by dt plus dou v by dou t. So there is an expression for as. So that is equal to, now ds by dt. What is ds by dt? Distance by time. Distance by time is velocity. So v into dou v by dou s, dou v by dou s as it is in place of ds by dt, that is v, plus dou v by dou t as it is. So as ds by dt equal to velocity v. If the flow is steady, that is dou v by dou t equal to 0. So velocity is not going to change with respect to time. So difference dou v equal to 0. So when dou v equal to 0, dou v by dou t equal to 0. This is for steady state. So expression for as equal to v into dou v by dou s. Now substituting value of as in equation 1 and simplifying the equation, we get PdA, just multiply dA inside, PdA minus PdA plus dou P by dou S into ds dA minus rho g dA ds cos theta equal to rho dA ds into as. That is a simplification. Just take negative terms to right hand side and make it positive. So, or else you keep as it is now for time's sake. So minus PdA minus PdA, that is going to cancel. So minus dou P by dou S into ds dA minus rho g dA ds cos theta minus that is equal to rho into dA ds into v into dou v by dou s. Substituting in place of as, v into dou v by dou s and simplifying. So now minus dou P by dou s into ds dA minus rho g dA ds cos theta equal to rho into dA ds into v into dou v by dou s, dividing by entire expression by rho into dA ds and taking negative signs to right hand side and making it positive. So dividing by rho into dA ds, we get dou P by dou s divided by rho. So that is dou P by rho into dou s plus g cos theta. So because rho into g dA ds cos theta divided by dA ds into rho, that then you can cancel rho into dA ds. So g cos theta is a remaining term plus v into dou v by dou s, so equal to 0. Upon dividing by rho into dA ds, we are going to get this simplified version and taking negative signs to the negative sign to make positive to right hand side. So we get expression dou P by rho into dou s plus g cos theta plus v into dou v by dou s equal to 0. But from figure we can see there, second figure, that is a small fluid element. So cos theta can be obtained as adjacent by hypotenuse. Adjacent is dz, hypotenuse is ds. So cos theta equal to dz divided by ds. So we can substitute in place of cos theta as dz divided by ds. Therefore 1 by rho into dou p by dou s plus g into dz divided by ds. Substituting in place of cos theta, dz divided by ds plus v into dou v by dou s equal to 0. Then taking 1 by ds or dou s common, so 1 by dou s into 1 by rho dou p plus g dz plus v into dou v equal to 0. So in this case either 1 by ds should be equal to 0 or dou p by dou s into 1 by rho plus g dz plus v into dou v equal to 0. But 1 by ds cannot be equal to 0. So possibility is dou p by rho plus g dz plus v dv equal to 0. That is, take it as expression 2. Equation 2 is known as Euler's equation of motion. Very important derivation, Euler's equation of motion. So ds cannot be equal to 0, 1 by ds cannot be equal to 0. So other possibilities, remaining expression inside a bracket. So make it that is equal to 0. So that expression is known as Euler's equation of motion. Very important derivation. Almost all like question paper they have asked this question. So it's a short question, very important one. So next, Bernoullis equation from Euler's equation. Bernoullis equation is obtained by integrating Euler's equation of motion. So if you know Euler's equation, then you can easily get Bernoullis equation of motion. Just you have to need to make integration of that expression, that is expression 2. So Bernoullis equation is obtained by integrating Euler's equation of motion as this Euler's equation of motion is given by dou p divided by rho plus g dz plus v dv equal to 0. Just integrate it. Integration of dp divided by dou p can be written as dp. So it's one and the same. Integration dp divided by rho plus g dz plus integration v dv equal to integration 0. So integration dp divided by rho plus integration g dz plus integration v dv equal to integration of 0 is not 0, it is a constant. So equal to constant. If the flow is incompressible, then rho is constant. So you know, for incompressible flow, rho is constant, density is not going to change. So rho is constant. So now you can take 1 by rho as constant from integration sign outside. So what is the integration of dp? Integration of dp is p. So p divided by rho plus integration of g with respect to dz. So g is a constant, you can take out. Integration of dz is z. So plus gz plus integration of v with respect to dv. So integration of v with respect to dv is v square by 2. So plus v square by 2 equal to constant. P by rho plus gz plus v square by 2 equal to constant. Now divide above expression by entire expression by g. So p by rho g plus gz divided by z, so that gz divided by g, so you are going to get z plus v square divided by 2g, so that dividing by g, so equal to constant divided by g. So constant divided by constant, that's g has value 9.81. So constant by constant, again you're going to get one more constant. So you can write as some constant c1 or c2 like that. Otherwise you can directly write constant only. So p by rho g plus z plus v square by 2g equal to constant. So there's an expression, Bernoullis equation. So here p by rho g plus z plus v square by 2g equal to constant. Above equation is Bernoullis equation. So very important, Bernoullis equation, in which p by rho g is pressure energy per unit weight of fluid or pressure head. P by rho g, you have to remember, it is pressure head or pressure energy per unit weight of the fluid. Why it is unit weight of the fluid? Because small letter w, that is specific weight, is given by rho g. So or it is gamma equal to, or small letter w equal to rho g. So pressure energy per unit weight of the fluid. Unit weight means, specific weight means weight per unit kg, or it is with respect to 1 kg. So specific weight, pressure energy per unit weight of the fluid or pressure head. V square divided by 2g, that is kinetic energy per unit weight or kinetic head. It is called as kinetic head or kinetic energy per unit weight. You know, V square by 2g is kinetic energy. Then z, that is related to some height. So z equal to potential energy per unit weight or potential head. It is commonly called as potential head or sometimes potential energy per unit weight. Bernoullis equation for fluids between points 1 and 2 is given as, so that you can apply this Bernoullis equation for points 1 and 2 or sections 1 and 2 as P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g. So this is an expression for the fluid flowing between points 1 and 2. So 1 corresponds to section 1 or point 1, then 2, that is for section 2. So you are not going to get rho 1 and rho 2 here because same fluid is flowing. So rho 1 equal to rho 2 equal to rho 1 is same fluid. So you need not write rho 1 and rho 2 here. So that is the expression. Then Bernoullis equation for fluids between points 1 and 2 is given as, so that's what I told, P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g. So P1 by rho g is pressure energy at section 1, then Z1 is potential energy at section 1, V1 square divided by 2g is kinetic energy at section 1. Similarly, P2 by rho g plus Z2 plus V2 square divided by 2g. Those are pressure energy, potential energy and kinetic energy respectively. Then assumptions. The following are the assumptions made in the derivation of Bernoullis equation. So these assumptions are very important. One thing in this chapter is Euler's equation, then Bernoullis equation, then assumptions. So the following are the assumptions made in derivation of Bernoullis equation. The fluid is ideal, viscosity is 0. We consider only pressure and gravity force, so viscosity is 0. Or it is ideal case, that is the fluid has no viscosity, it is not going to offer resistance to flow. Then the fluid is steady, so because steady means there is no variation of property, so the flow is steady. So for example, velocity is a steady, we consider steady flow, dou v by dou t equal to 0 because velocity remains constant with respect to time. So the flow is steady and continuous. The flow is incompressible. We considered density equal to constant, that is for incompressible. Density is not going to change. The flow is irrotational. There is no rotation of the fluid, so it is irrotational. The gravity and pressure forces are only considered. We considered gravity and pressure forces. You have seen that in figure. There is a pressure force acting PdA and P plus dou P by dou S into ds into dA, and there is a W acting and it is making an angle theta with respect to ds. So only pressure and gravity forces are considered. The equation is applicable along streamline only. So we derived expression for the flow of fluid along a streamline, yes. So it is applicable along streamline only. The velocity is uniform over the cross section. So that means velocity is not going to change, same value, uniform at all the points. Then limitations of Bernoullis equation. Practically, the fluid is not ideal. Hence, due to no slip condition, velocity at the fixed boundary is 0 and it goes on increasing away from the boundary. It means the velocity across the section is not uniform. So we assume velocity as uniform, but it is not the case here because of the no slip region, the fluid is going to stick to the surface. It may be a fixed plate. So it attains 0 velocity at the fixed surface. Then it keeps on increasing till it reaches free stream velocity. So this is the way you are going to get velocity profile. So velocity is not uniform. Practically, in addition to gravity and pressure forces, some forces like viscous force is also involved in the motion of fluid. So because of viscosity of the fluid, we have to consider viscosity force. So that is the case here. We only consider pressure and gravity force. So in addition to pressure and gravity force, there comes into picture the viscous force. When the fluid passes from one section to another, some energy addition or subtraction takes place. About this thing we are going to study in laminar and turbulent flow and as well as in minor and major head losses. So because of the flow from one section to another section, that may be one section 1 to 2, we may have some energy addition or subtraction inside the system. Then Bernoullis equation for real fluid, or it is called as modification in Bernoullis equation. So Bernoullis equation was derived on the assumption that the fluid is inviscid, that is non-viscous and therefore frictionless. So we assume fluid is non-viscous or inviscid, that means the fluid has no viscosity, 0 viscosity. It is not going to offer resistance to flow of fluid. Because of that, there is no friction. So it is not the case here. For real fluid, there is a viscosity, and because of the viscosity, we are going to get friction factor. So, but all the real fluids are viscous and hence offer resistance to flow. So there is a resistance to flow of fluid because of viscosity. Therefore, there are some losses in fluid flows, and hence in the application of Bernoullis equation, these losses have to be taken into consideration. Because of viscosity, we have friction. Because of the friction, we are having some energy losses in fluid flow. So we have to consider that energy loss. So Bernoullis equation for real fluids between points 1 and 2 is given as P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g plus HL. You can see here for ideal fluid there was no HL term because we assume the flow is non-viscous or fluid is non-viscous. Now here fluid has viscosity. Because of the viscosity we have friction. Because of the friction there is a loss of energy. So we have to add that loss of energy to make P1 by rho g plus Z1 plus V1 square divided by 2g, P2 divided by rho g plus Z2 plus V2 square by 2g equal, to add HL to section 2 or point 2 side, that is P2 divided by rho g plus Z2 plus V2 square divided by 2g plus HL. Because of the fluid flow through the section, we are going to get some energy loss. So that loss, you may ask the question, why you have to consider for section 2? Because the fluid is flowing from 1 to 2. Initially it has no energy loss, as eventually it flows from 1 to 2. Because of the friction we are going to get some energy loss. So when it reaches 2, there is an energy loss that should be added to the section point 2 in the expression. So P1 divided by rho g plus Z1 plus V1 square divided by 2g equal to P2 divided by rho g plus Z2 plus V2 square divided by 2g plus HL, where HL is loss of energy between points 1 and 2. Initially at point 1, energy loss is 0. So it starts flowing, fluid starts flowing. When it reaches to point 2, because of the friction, we are going to get HL as head loss. So this is for real fluid. For ideal fluid, there is HL is equal to 0 because there is no viscosity. In next video, I am going to explain about the problems related to head loss as well as related to ideal fluid. Okay, thank you.